Hi, this is Tim Walker. In the next 5 minutes, I'm going to present you our project, BLS12381 library for BitcoinSV. Our library is used for supporting Bitcoin zero-knowledge proof smart contract. This is the first implementation of BLS12381 curve pairing verification on Bitcoin. For platform-agnostic applications, the choice requires a trade-off between performance using BM254 and security using BLS12381. We will recommend using BLS12381 as it is more secure. Although it is slower than BM254, it is still fast enough to be practical. Curve BLS12381 is both pairing-friendly and effective for constructing ZK snarks. And here are the two equations of the curves. BLS12381 uses a twist to reduce the degree of the extension field by a factor of 6. So G2 on the twisted curve can be defined over FQ2 instead of FQ12, which is a huge saving in complexity. So the calculation of a pairing consists of two parts. First is a Miller loop, where we compute an intermediate function of the two input points using the function f and do it recursively. The second step is apply a final exponentiation. So here you can see this equation 1. We apply the function f to point g1 and point g2, and then raise the value of f to a large power c. Both of the steps are quite expensive, but there are some methods that can reduce the impact of both of them. First, we can reduce the number of pairings to 3. This equation 2 is a verifying equation, where alpha and beta are known at setup. So we can pre-compute the second pairing, E of alpha, beta, and replace alpha and beta with the pre-calculated value to save one pairing calculation. Second thing we can do is to use only one single final exponentiation. Like instead of calculating final exponentiation 4 times, we can only calculate it once in the end. Finding the inverse of a field element is an expensive operation. So implementations of the elliptic curve arithmetic try to avoid it as much as possible. So we use the affine coordinate. The basic idea is to represent the coordinates using notional fractions to reduce the number of actual division operations needed. To do this, a third coordinate is introduced and used x, y, z for the internal representation of a point. And we use the Jacobian coordinates to represent the affine point. Since the calculation contains modular, which is very expensive, a way to calculate modular that doesn't require division is using the Montgomery multiplication. So to calculate the modular multiplication operation, we first convert the multiplier into Montgomery form and then use Montgomery multiplication. Finally, we convert from Montgomery form back to the form that we want. This is mainly how it works. And here is the library structure and the API of our project. We have 3 pairs and also one pre-computed pair of parameters as input. Here is an example of how you can obtain the parameters using the Circom tool. So basically, you obtain these 3 files, the verification key, proof, and public. And you can see here, like the verification key file, it contains the information of alpha, beta, gamma, and all the other parameters. And here is a test case using the Circom language. Yeah, that's all. Thank you for listening.